I would like to welcome you here to this course that I'll be teaching with my colleague Nived Chebrolu, and we will both be giving an introduction here into concepts of mobile robotics and mobile sensing systems. And we hope you're going to join us here for this course, looking into various aspects of state estimation and action generation. So if you think about autonomous mobile systems or mobile robots, a lot of things can come to our mind. These are vehicles which can drive autonomously through the environment and solve tasks for us. This could be flying systems like UAVs or drones that, for example, fly in this example here over fields and inspect what's going on in order to assess the status. This can be satellites flying through space, and this can be autonomous cars which are driving on our roads. These all are autonomous mobile systems. That means systems which are mobile, so they move through the environment. They are autonomous in the sense that they can control themselves or can execute actions on their own, and for that they need to decide which action to execute. And in order to decide which action to execute, such systems typically need to understand what they see, what does the world around them look like. And therefore state estimation is also a key element in order to understand what the surrounding world looks like, so that we can allow those systems to act appropriately. So these are kind of different systems that we will refer here in this course to robots. So again, mobile systems equipped with sensor data in order to perceive the environment and with the ability to execute actions. So typically equipped with a computer that processes the sensing data and generates action from this sensor data, with the hope that this action brings the platform closer to its goal or to its programmed goal. For example, to reach a certain target location or to cover an area completely and perform an inspection mission. Or, for example, to clean your home or mow your lawn if this is the objective of that system. So these are tasks that those systems need to carry out, and they need to select appropriate actions that bring them closer to their goals. And if you kind of boil down all those things that I have said so far, it will actually boil down to two central questions. So first thing is, what is the state of the world? And world here refers not necessarily to our planet Earth, but to the surrounding in which the system operates and the state of the system itself. And the second question then is, which action should the system execute? And so these are two problems which are tightly coupled with each other. The first problem is something that we typically refer to as state estimation. So here we want to assess the state of the system or of the environment. And here we use sensor data, for example, cameras, laser range scanners, or other sensors in order to perceive what's going on, to interpret the data, and to derive that typically into some form of model. This can be a map of the environment, but can also be another type of model. And then, based on this information, based on this model, based on the sensor data, we want to select an action. And typically we want to select an action that brings the system closer to its goal, what it wants to achieve. This can be a place in the environment, so a kind of a physical location where the system should go to, or the goal can also be more abstract, that it has completed a certain task or has covered an environment or any other activity that the system may execute. And the state of the system influences which actions to execute, and those actions typically lead to new sensor data, so it impacts the state estimation problem. So we have this loop here, this dependent loop, that state estimation has an impact on the action selection strategy, and then the selected action again impacts what we are going to observe. And we need to take both things into account. So let's look into state estimation. What kind of estimation problems are we typically tackling? And we can boil things often down to two different quantities. The first thing is estimating semantic information, and the second thing is estimating geometry. Of course, this is a simplification. This doesn't cover everything, but it actually gives you a pretty good overview. So estimating semantics means understanding what we see. So for example, taking an image and understanding what we see in this image, what is in that image. So in this example over here, you see plants observed by a mobile robot driving over a field, and the system interprets what kind of plants it sees. So which plants are, for example, crops we want to maintain on the field, and which plants are weed plants that we may want to eliminate. So being able to understand what the system sees, what is a crop, what's wheat, is one of those semantic estimation tasks. The other task, which is also very popular, is estimating geometry. So estimating what the world looks like. This can be the geometry of the building, the 3D structure that the system needs to infer, to estimate, in order to build an appropriate 3D model of the world that is relevant, for example, for performing navigation tasks. And of course, both things can also be estimated together and can be fused into a geometric semantic model. That's also something which we see more recently coming up in the robotics community. And then based on those models, we can estimate what we should do. For example, trigger an action that eliminates the weeds. Or after we have built a 3D model of the environment, we can navigate through this environment using path planning algorithms, for example. So what are the topics that we are going to address in this course? So what will you see here? So we'll start with a short introduction, and given that most of the homework assignments which are done here will happen in Python, there will be a block on teaching you basic Python capabilities. So this is not needed for understanding the course itself, but in order to solve the homework assignments, you need to have basic Python capabilities in order to do that. And then we will start with the kind of main topics of that course. Will be a short wrap-up on probability, so a short probability primer to make sure all of you who are listening have an idea what the basic concepts are, what we need. This won't take long, but introduces you to some of the basic things like base rule, for example, or what does conditional independence mean, because those things are needed later on in this course in order to understand the derivations or the assumptions that go into certain models. Then we will look into the recursive based filter, which is a technique for recursive state estimation, or let's better say a framework. And this framework can have different realizations. For example, a particle filter is a recursive based filter. Same holds for a Kalman filter. Then we'll start into occupancy grid mapping. That means building a map of the environment, and it's a special kind of map structure, similar to an architectural floor plan maybe that you see, and we want to enable systems, for example, equipped with a laser scanner to drive through the environment, build such a model. Then we will look into locomotion. So how do we describe the motion of a mobile platform? We can do this geometrically, and we can also do that probabilistically. That means geometrically taking basically our model into account, where are the wheels, and if I put a velocity command to a wheel, how does a platform move forward? And then probabilistically taking into account that all those sensor information or those commands are affected by noise, and how can we model the probability distribution of where am I going to end up if I start in a certain state and carry out a certain velocity command, for example. We will also look into probabilistic observation models, so interpreting the observation, what our sensor tells us. For example, a laser range scanner may measure the distance to the closest obstacle, and the question is, what is the noise affecting these measurements? Is this simply a Gaussian noise, or is this something else? And formulating this in a probabilistic sense is something that we need later on for state estimation problems. And for that, we will look into extended Kalman filters and look into Kalman EKF localization, so a Kalman filter-based localization system, and then also into particle filters, which is a non-parametric state estimation techniques. That means we are not using explicitly a Gaussian distribution to represent the probabilities, but to use a sampled representation, which will then lead us to Monte Carlo localization, which is basically using a particle filter for localizing a system in the environment. And then we'll also look into kind of control. So this is done in sense of executing an action. So how can we control the platform so that, for example, it drives on a certain trajectory or keeps a certain state? And this is then kind of the lower level of the action selection, and the higher level of the action selection is typically uses planning algorithms such as motion planning, for example, A-star or Markov decision processes, and so that is the framework for making decisions. And then in the last step, we will look into classification system. This is kind of the semantic part. The part in the beginning was more the geometric part, and look into how can we estimate what we are actually seeing in our image data, for example, and looking into learning approaches for solving those perception tasks. And this is basically what we are going to cover in this first course over here. And I hope you stay with us and learn those topics and get a good start into robotics technology. If I say we, that's myself, Cyrill Stachniss, and my colleague Nived Chebrolu, with whom I will be teaching this course here jointly. Before we start diving into the concept and the actual techniques in that course, I want to say a few words about the more formal aspects here. So what are things that you need to do in order to take the exam and pass this course? This is of course only relevant for the students here from the University of Bonn, which take that course. Those of you who watch this course just on YouTube and are not enrolled in the University of Bonn, that doesn't apply to you. So what we require you is to solve homework assignments. So we will give out homework assignments via eCampus. So this is a university-based system for providing homework assignments and handling submissions. And you need to solve those homework assignments and need to get at least 50% of the points of those homework assignments. You need to have at least 50% of those points in order to get the exam admission. So you will not be allowed to take the exam if you don't achieve that. The homework assignments often include coding examples, so you need to program small examples or the techniques that we're discussing here in this course, and this will happen in Python. And therefore it's important that you have basic Python capabilities that you can also learn at the beginning of this course, but you probably have heard that already in your bachelor program. At least we started with that 2-3 years ago, so that you should have been exposed to Python a bit. If not, there's a playlist with videos that we have compiled which should give you a good first start into Python. The homework assignments can be solved in teams of 2, so you can team up with another student and submit your homework assignments together. That is totally fine, but please make sure that you don't split that up, whatever. The first 2 exercises done by the first student and the second 2 exercises by the second student. That's not the intention. The intention is that you solve all those tasks yourself together with your partner in order to understand what's going on, but it's often easier, especially in the beginning, to solve things jointly. Saying this, you can cooperate with your partner or collaborate with your partner, but limit the collaborations among groups. So we have really a zero tolerance on plagiarism, so you're not allowed to copy the homework assignments from a colleague or from another group. This is really unacceptable. You are not allowed to take the exam or complete this course. I will be very strict on that because it's something that I really do not accept if you copy your homework assignments from someone else. Again, a few words about the coding exercises. They won't be very tricky. They should actually be rather simple and allow you to implement the stuff that we discuss here in the course. You will get small frameworks and basically need to fill certain aspects of those frameworks. This will all be done in Python, which is today kind of the de facto standard for scientific programming and prototyping. So if you want to build a system that in the end runs on a real robot, you probably won't do that in Python, but Python allows you to prototype that and do that quite quickly. And therefore our exercise here in Python, and we also have compiled a website which you see down here where you find a few videos if you need an introduction into Python and get a good start here. With this, I say thank you very much for your attention for today, and we will now dive into the concepts of that course and start with a primer on probability theory and try to get you up to speed or kind of level out that all of you who attend that course have the same basic knowledge on which we then can build on top. That's it for now. Thank you very much for your attention and see you in the next course. Thank you.